You take the elevator every day. You press a button. The doors close. You rise. You arrive. It's simple, routine, unremarkable. But what if that same idea, a vertical path between earth and sky, could carry you not to the 50th floor, but to space? Not a rocket, not with fire, not with explosions, just up, slowly, quietly, like climbing a rope into the stars. This isn't science fiction. It was dreamed by scientists over a century ago. It's been studied by NASA, ESA, JAXA, and if we ever build it, it will be the largest structure ever made by human hands. Larger than all the pyramids, larger than Mount Everest, larger than every bridge, tower, dam, and city combined. And yet, no one has built it. Why? The idea of a space elevator didn't begin with rockets or satellites. It began with a man who believed humanity could reach the stars without burning fuel. In 1895, Russian scientist Konstantin Tsiolkovsky stood atop the newly built Eiffel Tower in Paris. He looked up and imagined a tower stretching from Earth to orbit. Not a building, not a monument, but a cable, thin, strong, endless, connecting our planet to the heavens. He called it the Celestial Castle. At the time, it sounded like madness. Steel couldn't support its own weight at such heights. Materials didn't exist. Computers were decades away. But the vision stuck, and nearly 70 years later, another genius picked it up. Yuri Artsukhanov, a Soviet engineer, refined the concept in 1960. He proposed not a tower rising from the ground, but a tether descending from orbit, an anchor on Earth, a counterweight beyond geostationary altitude, and between them, a ribbon, thinner than a pencil, stronger than steel, stretching 100,000 kilometers into space. That's the modern design, and it still hasn't been built. But why? The secret lies in balance. A space elevator doesn't need to push upward. It needs to hold itself taut. Here's how it works. A satellite, or massive object, is placed in geostationary orbit, 35,786 kilometers above the equator. From it, a cable descends toward Earth. Another cable extends outward, past the orbit, into deep space, acting as a counterweight. The centrifugal force of Earth's rotation pulls the outer end outward. Gravity pulls the lower end down, and the two forces meet in perfect equilibrium. The cable stays straight, stable, untouched by wind, untouched by weather. Now imagine a climber, a robotic vehicle, ascending this cable. No rockets, no combustion, just electricity, solar power, magnetic rails. It climbs slowly, at 200 kilometers per hour. It takes 5 days to reach orbit, but it carries 1,000 tons of cargo for less than 1% of the cost of a rocket launch. That's the dream. And the nightmare? Finding something strong enough to hold it. Steel won't work. It snaps under its own weight at just 100 kilometers. Kevlar? Too weak. Carbon fiber? Still too heavy. The only material known today that even comes close, theoretically, is carbon nanotubes. Imagine a single molecule of carbon arranged in a tube, just one atom thick. Longer than any human-made structure. Stronger than diamond. Lighter than aluminum. And yes, in theory, strong enough to form a cable from Earth to space. But here's the problem. We can make tiny pieces. A centimeter, a meter, even a few meters. But we've never woven a continuous strand longer than 100 meters. And we need 100,000 kilometers. One unbroken thread. Without a single flaw. Not one missing atom. Not one defect. Because if there's a weakness anywhere, the entire structure collapses. Scientists have also explored other materials. Diamond nanothreads. Graphene ribbons, boron nitride nanotubes. Even spider silk, spun artificially, has been tested for tensile strength. None are ready, none are scalable, none are proven. We don't lack imagination. We lack the material. And until we can grow a kilometer-long nanotube without flaws, the space elevator remains a sketch on paper. It can't be built anywhere. It must be anchored on the equator. Only there does the Earth's rotation match the orbital speed needed to keep the cable taut. So where? French Guiana, somewhere near Kourou, home of Europe's spaceport, or the coast of Africa, near Gabon or Kenya. Perhaps an artificial island in the Indian Ocean, or Indonesia, near Sumatra. All places with stable geology, low seismic activity, and minimal storms. But here's the deeper question: who owns it? If it stretches from Earth to orbit, does it belong to the country beneath it? To the company that builds it? To humanity? What happens when a terrorist cuts the cable? What happens if a meteor strikes it? What happens if a rogue state hijacks the climbers? There are no international laws governing a structure that connects two worlds. No authority. The Outer Space Treaty of 1967 says no nation can claim sovereignty over space. But what about a cable hanging from it? The legal vacuum is as vast as the sky itself. Even if we had the material, nature would fight back. First, the atmosphere, weather systems, hurricanes, jet streams, turbulence. The lower 20 kilometers of the cable would be battered daily. Wind speeds over 200 kilometers per hour, ice forming on the surface, lightning striking repeatedly. Then, the radiation belts. Between 1,000 and 10,000 kilometers above Earth lies the Van Allen belt, a ring of deadly charged particles. Any human passenger passing through it would receive a lethal dose of radiation in hours. Even robots would suffer electronic failure. To survive, climbers would need to travel through it in under 48 hours, fast enough to avoid death, slow enough to not tear the cable. And then, the Coriolis effect. As the cable rises, Earth rotates beneath it. The top moves faster than the bottom. This creates a sideways pull, a gentle sway. Over time, the cable begins to oscillate, like a guitar string, like a pendulum. Left unchecked, those oscillations grow, until the cable swings across the sky like a giant whip. One misstep, and it could strike a satellite, or a plane, or a city. NASA simulations show that without active damping systems, the cable could become a weapon, not by design, by physics. The upper end of the cable needs mass, not just any mass, mass that keeps everything taut. So engineers propose two options. Option 1, a large asteroid. Capture one, tow into orbit, anchor it to the cable. It would be hundreds of millions of tons. Stable, permanent. But how do you capture an asteroid? How do you move it? And what if it drifts? Option 2, a space station. A massive artificial platform built in orbit. Habitable, functional, used for manufacturing, research, storage. It wouldn't just be a counterweight. It would be a city in the sky, a hub, a gateway, a new civilization. But building it would require thousands of launches, which defeats the purpose. Unless the first climbers bring the parts. And the first station is assembled robotically, slowly, over decades, like a seed growing into a forest. Let's talk numbers. Rockets cost $10,000 per kilogram to orbit. The International Space Station cost $150 billion. A single SpaceX Starship launch costs $10 million and carries 100 tons. The space elevator? Estimated construction cost, $10 to $40 billion. Annual operating cost, less than $100 per kilogram. Once built, it pays for itself in months. It would replace all existing launch systems. No more fuel, no more pollution, no more debris, no more failed missions, no more waiting for launch windows. You could send people, supplies, solar panels, water, fuel, buildings, factories, cities, to the moon, to Mars, to asteroids, with one machine, one cable, one promise. So why haven't we started? Because we're waiting for the material, waiting for the funding, waiting for someone else to do it first. We've landed on Mars. We've sent probes beyond Pluto. We've seen black holes. We've heard gravitational waves. But we still can't make a thread strong enough to climb into space. Is that really so hard? Imagine 2070, the year NASA predicts the first space elevator becomes operational. It rises from a floating platform in the Pacific, stabilized by thrusters. Its base glows with solar panels. Climbers glide silently along its length, powered by lasers beamed from below. Each one carries 500 tons. Every week, every month, the cost of reaching orbit drops below $100. Tourists pay $50,000 for a ride to space. They watch Earth shrink. They see the curvature. They feel the silence. They cry. Scientists deliver quantum computers to orbit. Manufacturers build zero-gravity factories. Asteroid miners use the elevator to ship water ice from the moon. The moon becomes a refueling station. Mars becomes reachable in weeks, not years. We stop calling it space travel. We call it commuting. And Earth? Earth stops being a cradle. It becomes a home, a place we leave, not because we must, but because we want to. And the cable? It stands, silent, unbreakable, a monument to patience, to persistence, to the belief that some dreams are worth waiting for. The space elevator isn't about technology. It's about mindset. We built pyramids without machines. We crossed oceans without GPS. We flew without wings, and then we learned to fly. We went to the moon with computers less powerful than your phone. And now we stand before a challenge that doesn't require magic. Just time, just money, just will. We don't need to invent new physics. We don't need to break the laws of nature. We just need to make a thread. One thread, longer than any human has ever made. Stronger than anything we've ever touched. And if we do, we won't just open space. We'll change what it means to be human. We'll stop seeing the sky as a barrier and start seeing it as a door. And one day, children will ask, how did they used to go to space? And their parents will answer, they burned fuel. They exploded. They risked everything before we just climbed. We hope this journey ignited your curiosity. Stay with us as we explore the structures that might one day connect Earth to the stars. Subscribe and join us for the next discovery.